Welcome to the Talon Talks podcast from Embry-Riddle Aeronautical University. I'm Alan Caesar. My guest today is Dr. John Maris. He's founder and president of Advanced Aerospace Solutions and Marinvent Corporation. But not only that, he's been inducted to the Canadian Aviation Hall of Fame. He's chair of the Royal Aeronautical Society of Montreal. He's a fellow of both the Royal Aeronautical Society and the Canadian Aeronautics and Space Institute. He's also associate fellow of AIAA and ISASI. Did I get that right?
Society of Experimental Test Pilots, SETP.
Yeah, I see. My mistake.
SETP.
SETP. All right. You're also among the rare triple alumnus from Embry-Riddle. You have a master's in aeronautical science from 1982, master's in aviation management from 1983, and a doctorate in aviation earned in 2017. And you're also on the industry advisory board for our College of Engineering in Daytona Beach. John, thanks so much for joining me today.
It's my pleasure, Alan. Thank you very much for hosting me.
All right. And thanks for that correction right off the bat. That's great. So you established Marinvent in 1983, which is the same year you completed your second master's. So thinking back to when you were doing that, what did you have in mind that your company would do? And what was sort of your goal starting out?
It was a very ambitious goal. I was dating a girl in Florida, and I was an immigrant or a student on a student visa, and she had not yet decided to marry me. So I had to sign up for the extra master's degree in order to keep my residency in the States legal. And 1 year is what it took. And we got married at the end of that year. She had agreed to marry me, which she was reluctant to do the year before. And so in 1983, I got married, joined the Canadian Armed Forces, and started Marinvent all at the same time. So the lofty goal of Marinvent was to entice my wife to get married and start a company at the same time. Now, things did evolve from that a little bit, but I have to be honest about how it began.
Fair enough. So, yeah, what did it? Now, you obviously weren't stocking shelves at Loblaws while you were getting this company going, but what was it that took it to actually get it off the ground?
The breakthrough for Marinvent was I was an active pilot, a commercial pilot, flew commuter airlines, and I was whenever I was in a junior position, I was the one in charge of updating the aeronautical publications, the Jeppesen charts, as they're called in the industry, which is, think of 30 volumes of phone directory pages that are updated page by page by page. And it seemed to me that it would be better if we tried to make that available in an electronic format. Bear in mind, when I began, this was actually in the early 90s, cell phones were kind of a new thing. Most people didn't have cell phones. I can say for a fact, most people did not have a CD reader in their office equipment. It was all floppy disks, right? So to say, why don't we electronicize the charts, required basically a complete rewrite of software that could do it with very limited computing power. And it turns out that coincidentally at that time, the USSR had collapsed, and there were available scientists with incredible programming prowess that could, for basically the kind of money that I could afford at that time, help me develop an electronic platform for Jeppesen charts. And we started that work in 1992. We launched in 1996 at Oshkosh, and it became the world standard for aeronautical charting. In fact, if you see a Jeppesen chart anywhere, it's basically software that was developed by my team, including those Russian scientists, who still work for me today, actually. So it's a very long-standing relationship. And it was a sea change for the industry, because for one thing, it basically launched what we call the electronic flight bag industry, the EFB industry. It was effectively the key application. There are people who have been dabbling with what to do with an EFB, but when you could suddenly put every chart in the world on a tablet, it changed the industry completely. And now, of course, the paper product is hardly anybody uses paper anymore.
Right. So 40 years is a long time to be in business. How do you weather ups and downs in the market and stay on top of like technology, especially in such a high tech world as aerospace, where things should be advancing fairly quickly? There's always the push of commerce.
Yeah, there is. But aerospace is a kind of an interesting conundrum, because we're both very aggressive and proactive while we're also incredibly conservative. Ask yourself why every airliner in the world looks the same as every other one in the world today, right? There are very few airliners where the tail's on the front and the engines are, facing backwards or forwards, whatever. So how do I stay up to speed? I involve myself, first of all, in academia. So the PhD was a golden opportunity to interact with absolutely the cream of leadership in my industry, technical and operational, and the professors. I cannot overstate the importance of that aspect of a PhD program internationally. And it's led to friendships and professional relationships that I absolutely value and keep to this day. The other thing is I belong to innumerable committees. Every time you say I'm a fellow of this or associate fellow of that, that's a symptom. But the reality of it is I belong to those groups and partake in the committees, the briefings, the conferences. So that's a path. And the last one is I'm a practitioner. I'm still an active test pilot. I'm delegated by Canada to do flight test and flight analyst work. So I'm always seeing the latest avionics, the latest synthetic visions or enhanced visions or pretty much any technology that comes down, I will eventually see and have to test fly. So those three factors are what help me keep current.
Tell me a bit more about being a test pilot. Like, what's it like to get your hands on the latest and greatest? Is it the greatest?
Well, I've always wanted to be a test pilot, and not because of the sort of the right stuff image. I had wanted to be a test pilot long before the movie came out. A test pilot combines certain qualities that are a little different than a line pilot. One is we are like an ambassador and a translator between the engineering divisions of a company and the flight operational pilot divisions. Pilots say, well, it flew a little funny, and the engineers say, well, what was the CN beta like? Well, that's one of the jobs of the test pilot. In fact, two of the jobs of the test pilot are, number one, understand what those words mean. Number two, translate them into particular flight test techniques. We call them FTTs, flight test techniques, where we're going to test the CN beta doing things that a regular pilot has never seen. Now, they don't necessarily require extraordinary skill, but they're just things that you haven't seen before, okay? And so you learn all these things. That's why when you go to test pilot school, I went through the military one at Edwards, the United States Air Force Test Pilot School in 1988, you're taught all these FTTs, these flight test techniques. You're taught the math that's underneath them, that underlies them. You put them into practice, and then you write the reports. And then the next thing that a test pilot has to do is convince the people that are paying them why their product is no good and they have to change it. So you have an incredibly challenging moral dilemma of you're being paid by the very company whose product you're trying to critique, right? So your level of integrity and professionalism and how strong a case you can make means a whole different set of training. The last ingredient is, and this happens quite often, is you're going to be flying an airplane that no one's ever flown before. And so you're going to strap yourself in and light the blue touch paper and see what happens. And so you have to build a skill set that makes you more flexible, perhaps, than others. So, for example, I flew left seat the same day in a C5A, doing things that the captain hadn't seen before. Flew the Goodyear blimp the same day, and went solo, not the same day, but the same week, in an aircraft, a single-seat fighter aircraft that I'd never flown before, had no dual and no simulator time. Now, to put a perspective to a civilian pilot, when you're flying a Cessna 150 and you want to fly a Cessna 172, the flying school will make you do 3 hours of training and a checkout and a this and a that and the other. Here, they're sticking you in the left seat of a C5A and having you do things that the guy who's actually in command hasn't seen before, and yet it's part of the job.
Does that make you nervous at all?
No, not because of extreme bravery or anything else. I mean, I've had my fair number of surprises, let's call them. I think number one, you're very busy doing a job, and it's not that it's intrinsically very, very dangerous. In fact, the one that most people think is the most dangerous flight is the first flight, right? Well, no one's ever flown this thing. We're going to wheel it out. We're going to light the engines and take it off, and God help all of us and hope it flies. Actually, that's not a very risky flight because what are we doing? We're in the middle of the envelope. It's a short flight typically. We're extraordinarily cautious. We've bound every error that we possibly can. We're carrying parachutes. We've got all kinds of monitoring from the ground. Those aren't typically the flights that are the high-risk ones. The high-risk ones are the 110th repeat of the same old thing that's always been really mundane. and never has given any trouble. And everyone's taking it for granted. The telemetry guys have their feet on their tables, drinking their coffee, and then suddenly something untoward happens. So actually, what scares me in flight testing is not, quote, the dangerous missions, it's complacency. That's what's scary about flight testing, not the dangerous missions. You are so tuned in, you're so practiced, you're so rehearsed, you do everything you can to minimize the risk, right? I don't think there are a lot of clumsy sword swallowers out there. And if you go, are you scared of swallowing a sword? You go, well, no, I practice really carefully and I've got it down. I'm much more worried about cutting myself, when I'm out in the garden with my machete trimming the hedge,
Right. So you came to Embry-Riddle for, I believe, a homecoming at some point. You brought this, it was a Piaggio Avanti.
Yeah.
This plane that you brought. Tell me a bit about that and why it existed and what you were doing with it.
That's a great series of questions. The Piaggio Avanti is actually one of the most beautifully inspired aerodynamic designs. Its efficiency is just off the clock in terms of what it would do. We used to make a joke that if it could climb any higher, it would put fuel back in the fuel tanks when it was cruising. It was an incredibly efficient machine. It also is the world's fastest civilian turboprop. So here's an airplane with propellers that can go to 41,000 feet at 2/3 the speed of sound, which is a pretty impressive, and it does it silently from inside. We picked the Avanti for a couple of reasons. We needed an incredibly efficient airplane because we wanted to fly for a long time. We needed a very large cabin because we needed to put a bunch of test engineers and researchers and scientists in the back, probably with laptops. And most importantly, we needed an airplane that could be flown single pilot. Why? Because we would do some very strange things to half of the airplane cockpit. And we didn't want to be experimental because that puts too many constraints on what we can do, who can be on board, where we can fly, this kind of stuff. So when you look at the list of large cabin, fuel efficient, single pilot airplanes, it comes down to basically a couple of airplanes. The Piaggio Avanti was one, and the Beach Premier, which is discontinued, was another one that we test flew, and the Avanti won out. A lot of very good aircraft didn't fit the bill because they violated one or other of these requirements. So for example, Learjet is not very fuel efficient down low, and it has a tiny cabin and requires two pilots. Citation can be flown with one pilot, but again, the cabin is very, very small compared to the Avanti for the price. Now, something like a Gulfstream has a huge cabin, but it needs two pilots. So when you take away all those constraints, what did we do with it? We loaded the airplane up with computers, simulation equipment, interfaces, broadband telemetry, to the point that we could fly this airplane from an iPhone, and without the airplane being experimental. So a lot of people say, well, that's just not possible. Well, just it was. And we flew with the head of NASA, and we went through the entire NASA safety protocols, the Johnson Space Center safety protocols, to get it approved. And we sailed through it. We had no issues getting it approved because we had done our homework.
Okay. So when you say fly from an iPhone, you mean are you holding the phone up like using the internal accelerometers as a sort of a stick and rudder thing?
Almost. You got to be a little careful. We were using the phone as a kind of a mouse input. If you use the phone as an accelerometer, the problem is that it's in the thing that's accelerating, so you get feedback loops. You get feedback loops that you don't intend, right? And if you drop the phone, it could lead to interesting repercussions on the airplane. Of course, we safeguarded the plane from all those things. So we actually only controlled the plane in roll, and we wouldn't let the phone let the airplane do more than the autopilot maximum bank angle, which was 28 degrees. So the worst thing that could happen is you'd enter a gentle turn. Worst, if the phone short circuited and caught fire, you're in a gentle turn, perhaps. And the default was the airplane would roll level.
Okay, that's cool. So as we're recording this, you've got a talk scheduled with the Royal Aeronautical Society that you'll be giving on aerodynamic drag. And there's this photo you have on the flyer of this thing. I mean, it probably hints at the tone of the talk. It's a boat, and this thing's got 3 sets of wings on it, and each set of wings has 3 wings. Did it actually fly? What is this thing? Tell me about it.
So the Caproni Trans Aero, you have to agree, it's both stunningly beautiful and breathtakingly ugly, both at the same time, isn't it?
I definitely agree with half of that.
Yeah. So Mr. Caproni had a vision. Effectively, this airplane had a wingspan like a large airliner today. He had visions of flying across the Atlantic in this thing. Unfortunately, the state of knowledge of aerodynamics at the time kind of led Mr. Caproni astray, which was unfortunate. This airplane weighed about 60,000 pounds, which, in this day and age is not particularly heavy, but at that time, we're talking not far different from Wright brothers era. They didn't have airplanes of that size. It could take 100 passengers. 100 passengers. And the reason I have that particular picture in my drag talk is the talk is centered on things that we now take for granted, and we know what an airplane looks like, right? They all look the same because they've all been optimized around the same sets of aerodynamic rules. But at the time the Caproni came out, we had no idea. And 1921, I think. So they made the wings impossibly thin for a number of misguided, although well-intentioned reasons, which meant that this thing is full of struts and bracing wires. I would hazard that the drag of this smallish airliner exceeds the drag of a 747 in absolute terms, not relative terms, because one of these struts or cables has a drag coefficient of roughly 24 times as much as an airfoil does. So although they're not as big as the airfoils, when you add all the acreage of wires and stuff. So anyway, Mr. Caproni flew this thing, and well, he didn't fly it, his test pilot flew it. And on the first flight, it flew. It got off the water and it flew. But it had a severe tendency to pitch up, which is fair enough. You learn as you go.
Yeah.
On the second flight, it pitched up uncontrollably, and I don't know the whole story, but the understanding is that they had put ballast in the front of the thing to keep its nose down. And as the thing took off, allegedly, the ballast slid to the back. So not only did it have a pitch up tendency to start with, but now you had a grand piano sliding to the back of the vehicle that pitched it up big time. And it did what you might expect. All 9 of the wings decided to quit flying, and the thing fell onto its nose in a lake. The pilot survived, and it crumpled the nose and did some damage to the wings. Unfortunately, in the effort to tow it back across the lake to the home hangar, they completely destroyed the machine during the towing operation. I mean, completely, totally wrecked it. And Mr. Caproni gave up on this endeavor. Went on to a successful career in aircraft design, but that particular one, the CA-60, was finito at that point.
So why did it have so many wings? And that seemed like, so why don't biplanes and triplanes exist anymore? And why did they exist back then?
Yeah, another very good question. It all stems from early tests done with small wind tunnels. The Wright brothers are well known for having a wind tunnel. I mean, incredibly far ahead of the game to be testing what they did in a wind tunnel. I mean, we again take it for granted, right? There's a concept called Reynolds number, which is a non-dimensional number. It has no units. It's like a ratio, which is like Mach number for speed of sound purposes. And Reynolds number tells you how the airflow will behave in regards to laminar and turbulent flow. For those that aren't aerodynamicists, if you see a cigarette being lit, you'll see that the smoke initially climbs nice and straight and parallel vertically, and then seems to break down and then go into these eddies and circulation. And effectively, that's called a transition point where the boundary layer goes from smooth to turbulent. Well, that on a wing makes a humongous difference. And Reynolds number depends on the size of the thing you're testing. It also depends on air density. It depends on viscosity. But given that the density at sea level is fair enough for an airplane that flies low down, and the viscosity is about the same as the airplane will experience, the Reynolds number is directly and proportionally affected by how big the wind tunnel is. So if you put a 10th scale model in a wind tunnel, your Reynolds number of what you're testing is off by a factor of 10. And what does that mean? It means your results don't scale at all. So in my lecture, I have some sample Reynolds numbers. An airliner might have a Reynolds number of the order of 1 billion. But when you get to very, very small Reynolds number of the order of 100, the answers you come up with are the best airfoil is a super skinny thing like a membrane, like a bat's wing. And in fact, the bat is designed to fly at low Reynolds numbers. So is a dragonfly or a bumblebee, right?
Sure. So
all of those wings have that sort of gossamer quality, don't they? But the characteristic of all these things is they don't fly very well. You don't see a lot of bumblebees soaring in the breeze and gliding in effortless circles. They thrash the air. They thrash the air into submission, right? And flying squirrels are great as long as they're flying downhill and not very far from the tree. And as for bats, I don't know what they do, but they're not renowned for their flying prowess, right? Mm-hmm. Well, that's what we did. We effectively designed our aircraft using the bat, bumblebee, dragonfly metaphor, flying squirrel metaphor, and we made our wings impossibly thin. In fact, to give you an idea, at the normal Reynolds number we're talking about, a NACA 0020 airfoil, which is a sort of generic modern airfoil, regular airfoil, flies better facing backwards than it does facing forwards, right? So that gives you an idea just how off your results can be when you've got the Reynolds number wrong. So everyone builds these incredibly thin wings, and what do? They don't give very much lift. They stall very abruptly, and they're a structural nightmare. Right? They're thin, so they have no strength, no rigidity. They don't resist twisting at all. So what do you got to do? Well, you've got to add struts and bracing wires. And so you end up flying this sort of grand piano flying machine, which is trussed like a bridge or whatever. And also unknown, because you didn't test at the right Reynolds number, the struts and wires have enormous drag. So an equivalent cross-section of strut or wire to the airfoil has a drag coefficient of roughly 24 times as much as the airfoil proper. So when you add up on the picture of the Caproni all the struts and wires, the drag of those things far, far, far exceeds the drag of the wings. And so you don't have very much power to play with. And the last couple of things that are relevant is because the wings are so thin, you can't put fuel in them. And putting fuel in the wings relieves them of bending stresses, bending moments. And that's why airliners put their fuel in the wings predominantly and have limits as to how low the fuel can be in the wings if you have fuel in the fuselage, because the wings are actually anti-bending because of the fuel. And so when you add all these things together, you get an incredibly draggy, structurally inefficient, fuel inefficient airframe. So if you look at this thing that weighs 50, 60,000 pounds, it's the size of a very small airliner, a Dash 8, something like that. And if you look at how many wings it takes to fly one of those and what shape they are, they're probably 1/10 of the wing area of this thing.
Yeah. Well, so did we just not know? Because I mean, the Venturi effect is, Bernoulli developed that like a long time ago. How did we not know, or at what point did we figure out how to be good wings?
Yes. So Dan Bernoulli, and every pilot groans when you raise, Bernoulli, you have to answer the questions on Bernoulli's theorem, right? He published it in 1738, right? Pretty much 300 years before we sorted out how to get in the air at all with an airplane. Oh, well, we had some gliders before then. But the concepts that Bernoulli espoused were in 1738. Leonard Euler, who's just one of the greatest mathematicians ever, turned Bernoulli's theorem into the equations for our flow in 1752, so just a few years later. In 1845, two gentlemen, Claude Louis Navier and George Gabriel Stokes, gave us the aforementioned, or not aforementioned, but the eponymous Navier-Stokes equations. Those equations fully define what a particle of air will do, where it will go, what velocity it will have, fully define it in viscous flow. That's a phenomenal accomplishment, and that was in 1845. So if they had digital computers back then, they could do the flow around any airplane that's subsonic or even transonic today. The only problem with those equations is we still can't solve them, and there's $1 million prize if you can come up with a solution for those. So the Clay Mathematics Institute has $1 million waiting for anyone that's listening to this podcast that has got a full solution to the Navier-Stokes equations. But the point is, in 1845, we had these equations. 1845, not 1945. Mm-hmm. And then in 1851, Mr. Stokes of Navier-Stokes discovered a concept that another gentleman, Arnold Sommerfeld, had called Reynolds number. So you got a guy citing a guy who picks another guy's name. And in 1908, Osborne Reynolds gave us Reynolds number, which I just talked about. And it was published in the Royal Aeronautical Society, in the Royal Society of London in 1883. So we're a century ahead of where meaningful implementations of these equations. In 1851, Mr. Stokes again came up with Stokes' law, and in fact, Stokes' law is the Stokes are the unit of kinematic viscosity in the centimeter gram system of measurement. So he finally did get a centimeter gram second system of measurement. So Mr. Stokes finally got his claim to fame. But all this was 50 years before the Wrights were doing anything, and it would have solved all of the problems for the next 50 years had it been applied properly.
So aerodynamics is still kind of an elusive thing. It almost seemed like a dark art for a while. It's hard to like eyeball something that would be aerodynamic. Like there's, the Ford GT40, famous race car from the 60s, looks, super fast, but it exhibits a lot of lift in the front end at high speed, which is not what you want in a car. You want it to stay on the ground. So, there's things that look fast and there's things that are fast in terms, in an aerodynamic sense, or efficient in an aerodynamic sense. So what's behind that sort of dark art, Yeah, I know it's a science. How do you get there?
Yeah, Alan, you raise a great point because I've always been fascinated that people that put this 7-foot spoiler on the back of their K car to address the mythical tail lifting tendencies of the thing at 47 miles an hour or whatever, and actually wreck the flow around the car while they're at it. I think we can clump aerodynamics into a number of different sectors. One is, what have we discovered empirically that seems to work? And quite often you can look at nature. Soaring birds, all of them without exception, have long, thin wings, or what we call high aspect ratio wings. Where do we see that in airplanes? Airplanes that soar, gliders. The U-2, which is effectively an overpowered glider to fly very high at very slow speeds. So we start to see aerodynamic equations which directly lead us to a particular form. So this long, thin wing is when lift at low speed is important. Obviously, for a fighter, that's not the primary consideration. Others can overwhelm that one. So we start to see what seems to work. Then sometimes we discover a concept that is kind of obvious in hindsight, but wasn't at the time. There's an aerodynamicist, Richard Whitcomb, who's one of my heroes from aerodynamics, and he discovered several things that we see every day now. Winglets was one of them, and the other one was a thing called area rule. And he found actually some older research that made the obvious conclusion that air, as it sees a vehicle coming, is more comfortable if the change of the shape of the vehicle cross-sectionally is smooth and constant, right? No sudden lumps appear from somewhere and then disappear and then make the air kind of try and fill gaps. And you go, well, airplanes are smooth and constant. Well, no, they're not. The air comes along to the fuselage, and it gradually sees the nose of the airplane. That's nice. It's a nice smooth transition. Then the fuselage is a cylinder, so that's great. But then out of nowhere comes this 100-foot wing, which is just an insult to the air, right? Not just aerodynamically, from the wing perspective, but in terms of cross-sectional area. And to make it worse, we stick enormous engines on the wing.
Yeah.
And then all of a sudden, just as soon as the air has got used to the fact that there's a wing there, it disappears. So the air has to somehow make up that void, if you will, and regroup. And just as it's got that sorted out, the tail shows up. And usually the tail is 3 components that are all in the same place. So Whitcomb basically said, why don't we aim to smooth that mess out? Mm-hmm. And a good example of that is the 747. It's got a hump for a number of reasons, and I've heard many explanations. But one aerodynamic one is, let's have the airflow hit the fuselage, see an expanding fuselage, and just about the time that the wing is starting to mess things up, let's make that hump go away so that the cross-section from the fuselage is decreasing just as the cross-section from the wings increases. And let's stagger the engines so that we, again, reduce the insult to the air by making the engines increase. First you see the inboard engines near the front, then the outboard engines. And then let's not put the fin exactly where the tail is, but let's stagger them to a little degree. And while the tail is showing up, let's really slim down the fuselage. So if you look at a 747 in that perspective, it has aspects of this area rule built into it very obviously. And if you see airplanes that fly transonically, you'll see them, they actually have a physically wasted fuselage. By wasted, I mean shrunken down in the middle. Airplanes like the B-58 Hustler, it's a beautifully elegant, and you can see that effect absolutely obviously. So it's a long answer, but we learn these things and then we apply them. And if you don't apply them, you see an airplane without area rule compared to the identical airplane with area rule, it's night and day in terms of their performance for the same engines.
Right.
So well, there's an art as well as the math, right?
Right. And there's some amount you can compensate with, by throwing bulk horsepower at something, which I think the Soviets did a lot of in the Cold War era, right? That's like they just strap more engines on the things, and eventually you make a brick fly.
Yeah, yes, it's true, but actually it's diminishing returns. There's an airplane that's in my talk called the Douglas Stiletto, which looks effectively like two airplanes strapped next to each other with the pilot wedged in, like literally just somehow they wedged him in between the engines. And that's it. There's a stick on the end and they put the tail on the end of the stick. Well, that airplane was supposed to fly 2,000 miles an hour. It's nothing but engine. And yet it was no faster than the contemporary fastest airliner, which looked like an airliner, but which had it was the Comber Coronado that had some understanding of area rule, and it had area rule bumps on the back of the wings that were these really strange looking protuberances, but they made the area rule stuff work, and it was as fast as this Douglas Stiletto. So we learn by our mistakes, I guess.
Yeah, I suppose so. Well, that's really cool, and I'm fascinated to listen to your talk. Listeners that want to hear the whole thing, you should be able to sign up at the RAES Montreal website. It's happening February 18th.
It is February 18th.
Excellent.
We'd love to have you on board. It's one of a series of lectures that we give that are designed to appeal to both the aerodynamicist practitioner and also the historian, the history buff. And all you have to do at the beginning of the lecture is decide whose team you're on. And that will help you decide things like bio breaks and everything else. So when the Aero stuff comes on, all the history guys can go and take a bio break or refill their water jug and vice versa. So, but it covers both.
Fair enough. All right. I'm curious, you've got a lot going on. Like, are you working constantly? How do you find personal time to separate yourself from your business?
It's a bit of a train wreck, actually. I don't have a brilliant work to business balance because I have difficulty saying no to projects that interest me. And the other thing is because I happen just by historical purposes, I have 3 airline licenses. I'm actually licensed on the 747 on my airline licenses. When you keep those 3 things current, the FAA and Transport Canada and EASA don't go, well, John, we understand you're not really an airline pilot and you're not really, you're very busy. So don't worry about all those things airline pilots do. They don't have that attitude for some reason that I don't understand. So I have to do the same check rides, the same training, the same simulators, the same everything, medicals, and they're not the same medical, right? When a Canadian doctor takes my pulse, it's not the same as an American one or an EASA one. And so I have to do everything in triplicate.
Is beats per minute in metric different than in standard?
I hate to conjecture on that, but I'll pick up on that to give you an example of just how awkward it can be. I would do a check ride, which would be three different check rides at the same time: an EASA check ride, an FAA, and a Transport Canada. I would fight every year or every 6 months to combine the check rides, and sometimes the flight safety would let me do it, and sometimes they wouldn't. And their answer was very legitimate. Some of the check rides have different requirements, slightly different requirements. Let's say I had to do a circling approach for one, but I didn't have to do a circling approach for the other. What happens if I'm doing a unified check ride and I fail that component? What does it mean when the FAA says, I didn't need to see that, and yeah, I know you failed it, but I didn't need to see it, so you're okay. But the EASA goes, I needed to see that, and you failed it, so you're no good, turn in your license. What am I? What's my status? So the solution was, take 3 check rides. And being a human being, my first check ride would be fairly competent and on top. And by the end of the 3rd check ride, which would be now, 12 hours of check ride, if I could taxi successfully, I would pat myself on the back.
All right, John. Well, on that note, we're going to take a short break and then we'll continue on to the lightning round. The Black Alumni Scholarship at Embry-Riddle was established as part of a grassroots effort by the Black Alumni Network and alumnus Edmund Otubula. It helps students to get past the first challenge they often face when completing college, which is paying for it. One of the first students to benefit from the scholarship is recent Human Factors graduate Imani Murph. She is now on course to complete her PhD and has distinguished herself as one of Embry-Riddle's most published recent graduates. She credits her success in part to donor-funded scholarships like this one. The Black Alumni Scholarship is a term scholarship, meaning it relies on continuous support from alumni and friends to make awards to deserving students. Visit crowdfunding.erau.edu to make your gift and show future generations that they have the strength of the Eagle community behind them. That's crowdfunding.erau.edu. Make your gift today. All right, John, now it's time for our lightning round. I'm going to give you 5 questions and you're going to give me 5 answers. Are you ready?
Do I have to remember all 5 questions at the same time, or are they one at a time?
We'll go one at a time.
Okay,
yeah,
then in that case, on that basis, because my memory is good, but it's very short.
Okay, sounds good. So if you could fly any plane ever made to any destination in the world, what do you choose and where do you go?
Very good question. They're mutually exclusive because the plane would probably be either the B-58 Hustler or the Mosquito, the World War II Mosquito, and they are kind of incompatible with the kinds of places I would like to go to. But I've read an awful lot about the Andes and some of the challenging strips out that way, so I would fly a Twin Otter, a DHC-6 into the Andes to take a look at what some of those amazing approaches are like.
Very cool, very cool. All right, if you could read only one book for the rest of your life, what would it be?
Read one book. Holy cow, that's a very difficult one because I try and read quite a bit and I don't have preferred books per se. I actually have to flub the lightning round aspect of that because I could give you a whole host of answers ranging from the Bible to Wikipedia. So I'll just take a fail on that question. How about that?
Fair enough. We'll take the Bible / Wikipedia and that'll be good. Who's your favorite cartoon character?
I would say it has to be Dilbert because he has an extraordinary grasp of what it's like out there. And in corporate America, particularly high tech, which is where he works, there's kind of the perception of what it's actually like, and he captures some really. I mean, he's had stories of things that have happened to me. I'll give you one example. Was when I was posted to the Canadian Space Agency, I was in charge of the Canadarm2 workstations in the early days as the lead on those. They had just installed electronic doors all over the space agency. And I said, "Oh, terrific. Okay, I need a pass for those." And it says, "Well, they won't be available for 2 months." So effectively, I could not get in or out of my workspace. And literally, even for bathroom breaks, I would have to get someone to hold my hand and walk me through the building. And both entry and exit were controlled. So it wasn't like once you're in, you could get out. You couldn't do either. And so the reason I bring it up in the Dilbert context is because Dilbert actually, I think, raised that specific issue as something that had happened to one of the contributors.
Yeah, that's definitely kind of the absurd thing you'd see in that comic. That's hilarious.
Yeah.
All right. Picture for me in your mind, you're a grilled cheese sandwich, like the most perfect one you could possibly have. You're about to take a bite out of this thing. What are you going to eat?
Instead of a grilled cheese sandwich? In other words, what is...
No. What's in it? What's it made of? What's the bread? What's the cheese?
Okay. How about the most unsporty answer you've ever got? I'm lactose intolerant and don't like cheese. So its main lacking ingredient would be cheese. So it would have pretty much everything you could put in a grilled cheese sandwich except the cheese. So we are reduced to bread and butter and whatever else. So it would have to turn into a ham and avocado sandwich. How's that for a pathetic response to a grilled cheese?
No, that's good. I appreciate the improvisation there. Yeah. Is that actually a sandwich that you like to have?
It's good enough. I would do that for sure. Yeah.
Okay. All right. So if you could live for a week as any person in history, so this is only a week, not as big a commitment as the book. If you could live for a week as any person in history, who would it be?
I'm not going to push this as a very religious comment, but I think it would be one of the disciples to find out, right? To find out what was going on. And I'm not taking a Christian versus any other stance. I mean, I could just as easily be Caiaphas or Pontius Pilate or it doesn't matter. I would love to have seen what was the scoop back then. I have a huge interest in all religions and their history and their comparative religion. What they mean, what it was like at that time. So what the interpretation means. I'll give you one very quick example. And again, I'm not proselytizing. I'm not trying to convert anyone. But the Good Samaritan story is not at all about doing good deeds, right? That's not what that story is about. It's about how the most appalling race of people that you can't stand, the Samaritans, are the ones that did the right thing, whilst the upstanding rabbi, etc., did the wrong thing and left the poor bleeding guy on the street. So the moral of that story is not about being a good Samaritan and being charitable. It's the exact opposite of how we interpret it. And if you don't have the context, you miss what the story is about. So I would go back and I would live some of those biblical times on either side of the fence, to understand what it was really like.
Yeah. Well, and it's been documented by a whole lot of different people in a whole lot of different ways. So it'd be interesting to be the person there actually eyewitnessing it and taking it.
Yeah, exactly. Just scientific curiosity as much as anything else, rather than just religious fervor.
Well, yeah, scientific curiosity is definitely something that appeals to Embry-Riddle folks in general.
Sure.
Right on. Well, thanks very much, John, for joining us for the Talon Talks podcast.
Well, it's been my pleasure, and I'd like to thank everyone at Riddle. It's been a really good time, and I hope people understand sometimes when I'm being a little bit tongue in cheek to take it that way. In my business at Flight Test, you have to be very careful with what people say literally. Sometimes it means things. So thank you very much, and I look forward to more of the same. And if people join me for the lecture, I'd be delighted to take technical questions that relate to the subject matter.
Rock and roll. All right. Talon Talks is a production of the Embry-Riddle Office of Philanthropy and Alumni Engagement and the students of Wicked Radio. We're coming at you from my office at Embry-Riddle Aeronautical University in Daytona Beach, Florida, and John's home outside of Montreal, Quebec. Is it Quebec?
Yeah, Quebec is good. I'd like to give a shout out,
Sure.
if I may. I didn't do that, but Edmund, who made the connections and everything else, and who I have a long history with, who I think does an outstanding job keeping the alumni involved and contributing. So I just wanted to add that if I could.
Yeah, Mr. Odarte, our network leader, and you guys met at one of our network events in Montreal before the pandemic, when we could actually see people in face-to-face, in person.
Yeah, we have. In fact, I've hosted, I think, at least 4 or 5 visits to Montreal, not just alumni, but I think associate deans and various other folks, professors, traveling groups. We've had many visits here. It's not very well known, but Montreal is one of the very largest aerospace centers in the world. It used to be number 3. It's a bit lower than that now, but it was the 3rd largest in the world.
That's great. Well, so this episode was recorded by me and edited by Cindy Puckett. Edmund Odarte is our program manager. Bill Thompson is executive director of alumni engagement, and Tony Brown is executive director of communications. If you'd like to share your thoughts about our show or suggest a guest to us, we'd love to hear from you. Visit alumni.erau.edu/podcast and click the feedback link. I promise your message comes directly to me. Thanks for downloading us. We'll see you next time.